this tutorial, we'll dive into a challenging project that will prompt you to utilize rich AI-generated information, machine learning embeddings, and more. The particular use case we're going to investigate is a video question and answer system. We'll see how we can query our analyzed video clips for information and retrieve detailed answers. To support this web application, we'll need to implement a number of AI and application systems, which we'll develop step by step together. More specifically, we'll be employing Vertex AI pipelines for object recognition, metadata extraction, frame analysis, and embeddings generation. Starting solely with our video as the input, we'll gather all the analysis outputs into a single JSON file. In this Vertex AI pipeline, we'll be doing some Python-based analysis ourselves, such as the extraction of metadata. However, much of the heavy lifting will be handled by Google's video intelligence services. Additionally, we'll be utilizing Vertex AI's Embedding APIs. Our generated JSON structured data will be stored in cloud storage before being brought into our web application. Speaking of the web application, we'll be using the Flask framework. Also, the application itself will need to make requests to Vertex AI APIs. Specifically, we'll be using a Vertex AI foundation model for visual question and answer, while also employing Palm 2 for text summarization. Just to clarify, the frameworks involved, we'll be developing most of these components in Python. On top of this Python, we'll be using Kubeflow as our preferred pipelining framework. When it comes to the Flask Web Application, we'll again use Python for coding in conjunction with some Scikit-learn. This will create a more manageable experience surrounding our embeddings clustering and embeddings distance calculations. So we have an exciting amount of work ahead. I believe you'll find this approach to be relatively low code, simple to set up, and yet easily adaptable to a wide variety of use cases. We'll provide the diagram file along with the demonstration code in the description of this video. Now let's get started with our project. The first step is enabling some APIs for this project. I'm going to navigate to the Vertex AI page and click to enable the recommended APIs. Having enabled the Vertex AI APIs, let's also turn on the Video Intelligence API. Next, we'll outline a pipeline in Vertex AI that will be crucial for transforming our raw video data into valuable insights. These insights will be output in a JSON format and can subsequently be used in web applications. For the Python development, we're going to need an IDE. For the purpose of this demonstration, we'll use the Cloud Shell IDE, but feel free to use whatever you like. We'll be defining our logic in Python and then running the Python code to compile the pipeline specification for Vertex AI. In this next phase, we're about to introduce a significant volume of code. Hold on tight, but don't worry. Taking the role of your code travel guide, we'll navigate through each component step by step, ensuring that you grasp what we're aiming for. Plus, you'll have the unique opportunity to observe this pipeline in action live within Vertex AI Pipelines, a surefire way to enrich your comprehensive understanding. Are you ready? Let's crack on with the definition of the pipeline located at the tail end of this file. For the sake of simplicity, we'll ignite this journey with just one video and hard-code it. You could easily switch to a dynamic approach by specifying a list of videos when executing the pipeline. What are the required tasks in our pipeline? We're going hunting for objects, identifying every entity in our video using the Video Intelligence APIs. We're compiling data like entity descriptions, start and stop timestamps, and bounding boxes for each video frame. Imagine tracking a ball in our video. By tracking it, we gather interesting insights like when exactly the ball appears and vanishes, plus its precise journey across video frames. Following that, we'll mine for metadata, helping us obtain information such as the frame rate, video duration, and resolution details. Next, for each object that we've discovered using the Video Intelligence API, we're going to generate images that display only the star, the object itself. From those focused frames that highlight the different entities in our video, we'll generate embeddings, transforming the images into numerical vectors that provide a deep semantic understanding of the image. We'll be depending on the power of the Vertex AI Multimodal Embeddings API for this task. Lastly, we'll weave our results together and secure save them as a JSON file in cloud storage. Before we dive in, let's create a bucket for our analysis. We're using the janegoodall.mp4 file in this demonstration, provided by Google as part of their documentation and quick start guide. To incorporate this video into our pipeline, we'll move it from Google Cloud sample data and pop it into our freshly minted bucket. Okay, with all preliminary conditions satisfied, let's dissect each of these tasks in detail. Notice the modularity built into the design of these tasks. That was no accident. Our intent was to enhance manageability and flexibility, making it easier for you to tailor this pipeline to your specific needs. At the very beginning of the file, we've mounted the Track Objects task backed by Powerhouse Google Cloud Video Intelligence package. Searching the library's catalog, you'll encounter an array of options. Our focus this time is object tracking, but it's worth noting the other incredible features at your disposal, such as detecting faces, logos, shot transitions, and text that can all be woven into your video analysis. Here, we chose to keep it basic, saving the list of objects and their attributes. This includes object descriptions, the degree of confidence in object recognition, time markers, and bounding boxes. Next up is the role of the metadata extractor, supported by the Python AV library. This swift task presents us with the video resolution, duration, and frame rate, all crucial details that will serve a pivotal role in the following stages. Up next is a task that, though somewhat complex, is quite intuitive. Essentially, it involves taking all the objects we've recognized in the preceding tasks using the Video Intelligence AI and extracting those into pictures, i.e., the bounded objects in each frame for us to analyze as images. We're getting the bounding information for those images and then extracting the image from the video. We read those frames, crop them, and save them as an image in our cloud storage bucket. In order to give these images unique names, since we'll have a lot of them, we'll base64 encode the information about that image, specifically the JSON structure with time, offset, and bounding box. These pieces of information will uniquely identify each snapshot of the entity in our video. Next, we'll save links to all these images as a catalog artifact in our Vertex AI pipeline. The last AI task involves generating embeddings. In this process, we'll open the image, base64 encode the image file, and send it over to the Multimodal Embedding API to get back embeddings. The only things that we'll be providing in that API call are some credentials and the base64 encoding of that image. The final task just brings everything together. We aggregate information from our recognized objects and embeddings and save them to a structured format, which we then export as a JSON file using the same base name as our original MP4 file. We're saving a little bit of extra data to this JSON file to give you more flexibility when you're experimenting with this stuff on your own. Ensure you have the Kubeflow pipelines installed to compile this pipeline, after which you can save the file to your bucket. Before running this pipeline, let's take a quick detour to the Vertex AI Model Garden to understand the Multimodal Embeddings API, a crucial element of this solution. This API generates a 1408 length embedding for each image. It has the capability to analyze both images and text, placing them into the same semantic space with the same dimensions. While in this demonstration the focus is on image capabilities, there is the possibility to extend to other modalities. After that detour and armed with this knowledge, let's go back to our pipeline and give it a try. We will import our compiled pipeline file from cloud storage. In the advanced options, specify a service account, such as the default Compute Engine service account for successful API calls. For the output directory, we'll use the same cloud storage bucket. Finally, let's run the pipeline and see this process in action. What's great about this pipeline view is that it outlines the flow of tasks and the interdependencies. Observe that as these tasks progress and finish, they output logs which can be viewed in the panel below. Do note this pipeline can take some time to run. As we inspect the summary, we can see it's already run for about 28 minutes and is still ongoing. That's partially due to the extract images task taking a while, which could potentially be parallelized for enhanced speed. We've also added static waits to the generate embeddings task to prevent overwhelming our quotas and running into errors. For your reference, in case you want to request a larger quota to expedite your pipelines, you can access the quota from the quotas page. Specifically, we're using the Multimodal Embedding API, and we're currently allowed to make up to about 120 calls to that API per minute. We've added a static wait, which conservatively puts us around the 50% quota mark. At the end, our results compilation reveals the output of our analysis. Jumping over to Google Cloud Storage, let's take a look at the video and the corresponding output. Note we're not going to watch this whole video, rather just show a few clips. It's a nature-centric 3-minute clip. In the output of our analysis, at the very top of the file, we have some metadata for the video itself. We have all those entity pictures and images that we extracted. We also have their embeddings and file location in Google Cloud Storage. What's exciting is that there's a lot of interesting information we can use when analyzing our videos. Simple analysis can yield understanding of entities involved in the video, where they show up, and where there are patterns occurring among certain objects. To take this even further, we're going to create a front-end application for all this data using Flask. At the top of the code, we import modules for the web framework, along with some utility modules for Google authentication and some Scikit-learn packages for clustering, as well as embedding distance calculations. Before initialization of our web app, we create a global variable data, which will be used in some of our API endpoints. It reads the JSON file generated earlier and carries out a clustering operation to group images into semantically similar categories. This doesn't pay attention to the timestamp, rather, it focuses on the actual content of the image to understand where there are frames with similar objects in our video. Naturally, there does tend to be a correlation. A frame and the following frame will often have similar entity characteristics. However, we're not relying on these temporal relationships to infer patterns around entities here. The next task in the pipeline is a tad complex. It involves assigning a cluster value to each of our embeddings, i.e. each of our cropped object frames. This process uses agglomerative clustering from Scikit-learn, which is a method that takes a distance metric, in our case cosine similarity, and recursively pairs up images that are closest to each other. We're specifying a distance threshold rather than an explicit number of clusters, allowing us to achieve a natural number of clusters rather than forcibly specifying the cluster count. There are other ways to calculate distance, such as Euclidean distance and different methods for clustering, like k-means, for example. However, these have been commented out as they can complicate the setup, but they are worth exploring if you wish to customize the process. For each of the images in each cluster, we'll get the base64 encoding up front, as we know we'll need it later. We thus pre-calculate these and store them in our data variable. All the metadata about the image embeddings, and the base64 encoding of the image will be stored in memory. Let's set up our static directory, which will contain some HTML, JavaScript, and our images. A multi-threaded copy operation imports all the images into our static images directory. Next, we set up a root for the root directory, serving up an index.html file that includes our CSS and JavaScript code. Most of the lines here are in the HTML head section, while in the body we set up a cluster selector and a field to allow users to put in a custom explanation prompt, allowing us to ask specific questions of the images we've extracted from our video frames. The JavaScript section is a bit more complex, starting with a function that is run when the Explain button is clicked. This function makes a fetch request, posting to our Flask app's API endpoint with the cluster we're interested in, as well as the user's custom prompt, before displaying the explanation in a div element. Further down, we handle the clustering logic on the front end. We group entities by the cluster value calculated using the agglomerative clustering. The remaining code deals with the user interface dynamics, allowing users to change the cluster they're viewing, load images, and scroll through them. Our front-end index.html file is good to go, so let's carry on with our Flask app. When we get the entities to initialize our front end with that JavaScript, we require the image pointer, which is the image URL, a relative URL, and the value for the cluster. We obtain this data from our data variable. We only send this necessary data rather than the full data variable to our front end, as it can be quite large and may affect performance. In our backend, we have an explanation API endpoint where we receive the cluster value and a custom prompt. For each individual image in the designated cluster, we analyze it by utilizing our image question answer API endpoint from Google Cloud, providing a response for each image based on the user's custom question. Once we have an answer for each image frame in our image sequence, we summarize the results across all frames using a standard large language model approach, powered by the PaLM 2 model in Google Cloud. We have some standard Flask boilerplate code at the end of our app. Before we proceed, we need to ensure that we have our data file and all the required libraries available. Let's also ensure our project configuration is properly set up. We'll be using the default authentication from the terminal. We might need a few attempts, but let's test our app and run it on port 8080. This allows us to use the web preview feature from our Google Cloud shell. It seems there's an issue with the bucket name. We should switch it to Video AI Demonstration, which is our bucket's name, and try to initialize again. After that change, we're up and running. Checking the web preview, it looks like we're off to a great start. However, as we navigate, it appears our images aren't loading in any of the clusters. We likely have the same issue, but in our front-end code. After adjusting that, reloading our web app shows the images. Each image loads as we click through, showcasing groups based on semantic similarity. We can choose from about 20 different clusters representing various entity types. We can further explore these clusters and also pose questions. Responses might take a minute as the AI examines the various frames of the image sequence. It then uses a question and answer approach on these images and leverages a large language model to summarize and synthesize the frame level information. For instance, when asking about the snake, the AI believes it to be slithering on a tree branch. Do note, however, that as with other generative AI systems, the AI can hallucinate. That said, an unanswerable response can come up if the AI doesn't have adequate context. Moreover, certain queries may trigger errors if they're perceived to be at odds with the system's safety and responsibility guidelines. Again, we'll share the diagram file and description code in the video description. Also, as a part of our AI tutorial series, we'll donate $1 to AI safety research for every 10 subscribers to this video. If you found this tutorial helpful, please consider helping the channel and AI safety researchers by subscribing or just donate directly. We hope this tutorial was useful and remind you to please enjoy responsibly.